Good morning. I welcome you all to this session of fluid mechanics. Well, last class we discussed the Euler's equation of motion, or the Euler's equation, that is the equation of motion for an ideal flow of an ideal fluid with respect to Cartesian and cylindrical polar coordinate system. So we derived from the principle of conservation of momentum applied to a fluid system, and we considered the fluid to be an ideal fluid, that viscous force was not present in the flow of fluid, and then derived the equation for motion, that is the conservation of momentum, with respect to a Cartesian coordinate, and then we converted it to a cylindrical polar coordinate system. Then we recognized the vector form of the equation of motion, and we also discussed this in cylindrical polar coordinate system, and we also discussed that this can be obtained also in different coordinate systems. So these equations were known as Euler's equation, that is the equation of motion for the flow of an ideal fluid. Now we will derive the same equation of motion, that is the Euler's equation, with respect to streamline coordinates or along a streamline. So let us see how does it look. That means if we consider the flow along a streamline like this, and we consider a fluid element in this streamline, let us consider this is the direction of this streamline. So at any point here we consider a fluid element like this, whose length is, for example, delta S along the streamline, and let us consider this area is dA, or simply A, not dA, cross sectional area is A, or del A, cross sectional area is del A, small fluid element, that is the cross sectional area perpendicular to this plane. Now this is moving at a velocity. At this point the velocity vector is v. I am not using the vector notation because now v here is identified as a scalar component, because this is always along the direction. When I take the streamline is the direction, things becomes one dimensional. That means the velocity at this point is along the direction of the streamline, that means along the tangent to this. So this is the situation. Now when we have assumed the flow to be ideal, that means the fluid is an ideal fluid, then the only pressure forces acting on the fluid is surface forces acting on the fluids are pressure P at this surface, and the downstream surface it is P plus del P del S into delta S. That means the change over delta S. That is the. Apart from this, what are other external forces acting on the fluid body is its weight, that is mass times the gravity. That means because of the gravitational body force field, that is rho into delta A delta S, that is the volume times G. Let us consider the angle made by this vertical line, that is the line directing the weight of the body acting the gravitational force, the line of action of the gravitational force, that is the vertical line, with the tangent or the direction of the streamline there along which the velocity exists. Let this to be theta, that means this angle, let this is to be theta. Then a simple force balance in this direction of motion can be written as, from the equation of motion or the conservation of momentum, whatever you tell, that mass rho times delta A delta S, this is the mass, times the change in velocity, let us write this as dV dt, is equal to the net force acting in this direction. And the net force acting in this direction is contributed by the pressure force and the component of the gravity along this direction. So therefore at this point if we write, the net force will be P into delta A in the small elemental volume minus P plus del P del S into delta S into delta A, well, minus the component of the gravity is in this direction, minus the rho delta A delta S into G, that is acting vertically downward, component is cos theta, that is if this be the theta, so this component will be cos theta. Well, now from a simple geometry we can write that if we consider this height of this element, that is this dimension, the vertical direction, this is delta Z, that means this is the vertical displacement from this point to this point or from this point to this point, delta z, then we can write cos theta is delta z by delta s. This is this delta z, that means this vertical displacement divided by delta is the length from a simple geometry. This triangle, if we consider a triangle like that, that means this is delta s, this is delta z, that means this vertical displacement between these 2 points is delta z. Delta z, delta s, limit of this, because theta is changing from point to point. If you define theta, the angle of inclination at any point with the vertical and the direction tangent to the streamline, that will be delta z, delta s tends to 0. Physically this is defined like that, which gets a mathematical shape as dz ds. That means with the change in s along the streamline, how the z coordinate is changing, simple common sense we can tell that is the inclination cos theta, that is the angle theta between the vertical and the direction tangent at any point to the line is dz ds, obviously. So if we substitute this value of cos theta here and make a simplification, you see p del a cancels, del s del a, del s del a, del s del a cancels from both the sides, then simply we get rho dv dt is equal to minus p del minus del p del s, sorry, p cancels out, minus del p del s minus rho is there, rho g dz ds, or we can write in another form that dv dt is equal to minus 1 upon rho del p del s minus g dz ds. That means this is the form of Euler's equation, that is a one-dimensional type of thing where v is in the direction of s along a streamline. So s is the coordinate along a streamline and v is the velocity along the streamline, because velocity will be always along a streamline. v is the resultant velocity of the fluid particle. This is the form. This can be also splitted as del v del t. Here you see that v is a function of s and t, one dimensional. V is a function of s, the coordinate along the streamline and the time. So therefore a simple split up of this substantial derivative in terms of its temporal derivative and the convective derivative is this. So therefore one can write this is equal to right hand side as it is, del p del s minus g dz ds. So these two equations, either this or this, are the Euler's equation along a streamline. All right. Now I will tell you the most important theorem in this context, which is very, very important in solving different problems, physical problems or applied problems, problems of engineering applications. This important theorem is known as Reynolds transport theorem, which is very, very important, Reynolds transport. Now I will come to, probably you can tell that this is the most important part of this section, which allows us to utilize all the conservation laws for analyzing fluid flow problems in practice. So for the time being, I just stop the discussion on conservation of energy. We have discussed conservation of mass and conservation of momentum. Before that, we discussed the Reynolds transport theorem. Now what is Reynolds transport theorem? Reynolds transport theorem. Now Reynolds transport theorem is a very important theorem, the proof of which is not that important, or I will not do here. If you are interested, you can see in any book, standard book. But what is more important is to know the theorem very correctly. Now if you see all the physical laws, for example the laws of conservation of mass, momentum, energy, this type of all physical laws, the thermodynamics law, thermodynamics second law, all physical laws are basically stated with respect to a system, or you can tell the birth of all physical laws have taken place with their implication or explanation with respect to a system. For example, if one is asked what is the definition of, what is the statement of Newton's second law of motion, what is the conservation of momentum? That is rate of change of momentum of a system or a particle. Particle is a differential concept of a system, or a system is a assemblage of particles. So it is the rate of change of momentum of a system or a particle which is equal to the force in the same direction. For example, the conservation of mass. Conservation of mass is defined that mass of a system remains unchanged. Nobody can tell that mass of a control volume remains unchanged. Whenever we tell that this conservation of mass principle, that mass remains unchanged. Mass of what? That mass of a system remains unchanged. It is neither created nor destroyed. Total mass remains constant. So the definition of system is inherent. For example, the conservation of energy. This energy of a system is equal to the energy of a system within it is equal to the total energy interacted by the net energy interacted by the system with the surrounding. So therefore the basic laws are first stated in terms of systems, but it has been found while analyzing the practical problems or even the problems, physical problems for the sake of academics, it is much easier to go for an analysis with respect to a control volume. So therefore, to apply the principle of conservation or any physical laws to a control volume, one has to know the statement for that. For an example, if I tell what is the law of conservation of momentum for a control volume, can you tell the rate of change of momentum for a control volume? Because control volume is a fixed. Control volume may move, that I will come afterwards. Control volume may move, even it can move with a changing velocity or with uniform velocity. But there is another provision that control volume is fixed. In most of the engineering applications, we take a fixed control volume. Well, so when control volume is fixed, the question of its movement doesn't come, so change of momentum doesn't come. So therefore the question comes that how would you explain the Newton's second law with respect to a control volume? Similarly, the conservation of mass, for the definition of a control volume, mass of a control volume may not remain fixed. So what will be the definition of the conservation of mass for a control volume? For the conservation of mass, without knowing any theorem, it becomes very simple from our simple intuitiveness that that mass conservation is like that. The net mass, the mass coming in minus mass going out is the mass which is being accumulated within the control volume. That comes from a simple intuition, but it may not be so for other physical laws. So Reynolds transport theorem is a theorem which helps us to relate, or simply we can tell which relates the statement of any physical law for a system to that for a control volume. That means it relates this, again I am telling, the statement of a physical law for a system to the statement of the same physical law for a control volume. How these two are related is given by the theorem known as Reynolds transport theorem. So without giving a proof here, you can see proof is not that important, but more important is to know the theorem very correctly. So I write this way, the Reynolds transport theorem. It tells like that in statement that rate of change, I write this thing, rate of change of any property, rate of change of any property within a system or for a system, better you write rate of change of property for a system. This rate means time rate of change. You can write time rate of change of any property for a system is equal to the rate of change, the ultimate outcome of this theorem, rate of change of the property, the same property, rate of change of the property, rate of change of the property. Here you write within a control volume, within a control volume, within a control volume plus the net rate of a flux, plus the net rate of a flux, plus the net rate of a flux of the property from the control volume. It is not a simple intuition, it has to be proved. For mass, it comes from simple intuition, otherwise it is not. So now I see that what is the definition that rate of change that transport theorem gives us, the time rate of change of any property for a system is equal to time rate of change. Here also rate means with respect to time, usually in physical system we usually means rate means with respect to time, is equal to time rate of change of the same property within a control volume plus the net rate of efflux of the property from the control volume. So therefore this equation relates the statement for a system to that for a control volume, and this is operative for any property which is an extensive property, for any extensive property, for any extensive property, any extensive property. So now if you look, this can be written for any extensive property. Well, you can see, so this can be written in a mathematical form like that. If we consider n as the property, n is the property, extensive property, and we defined eta as this property per unit mass, any property per unit mass, then this time rate of change of property for a system, we can write this definition is like this now, dn dt for a, now mathematical shape of this theorem is like that, system is equal to time rate of change of the property within the control volume. If eta is the property per unit mass, this first term on the left right hand side can be written eta rho dv, small elemental volume, it is over the entire control volume. Here I write specifically CV, not the V, because this implies the control volume where this implies the system, plus the net rate of efflux of the property from the control volume. You know how it can be written with mathematical symbol. If eta is the property per unit mass, it will be what? Eta into rho V dot. Now here I am not bringing n as the unit vector for a area because eta and n sometimes confusing. So simply I use dA as the vector. That means without writing n dA, sorry, here I write without writing n dA to show this as a vector, that dA is the scalar magnitude of a small elemental area and n is the unit vector along the normal to the area taken positive directed outwards. Without taking that, I simply use, sometimes it is used dA as a vector whose magnitude is the area, scalar magnitude, and direction is along the normal, positive directed outwards. So this is simply over the entire control surface, CS, it is control volume, is the net rate of efflux. So this for the second term in the right hand side, this for the first term in the right hand side. So therefore right hand side is the statement with respect to control volume, whereas the left hand side is the statement with, this is statement with respect to system, and this is statement with respect to this is the statement with respect to control volume. So therefore we can say now mathematical shape is like that. This is the rate of time rate of change of any property n in a system is the time rate, sorry I am very sorry, del t. So time rate of change of the property within the control volume plus the net rate of efflux of this property from the control volume. So now in steady state obviously this term will be 0. So for a steady state dn dt is equal to eta rho v dot dA, where eta is the property per unit mass and n is that property. So therefore you see for a steady state automatically this will become 0. So this is the mathematical form of the equation. Now let us apply this for different cases. Now first of all we want to apply this for conservation of mass. Let us consider the conservation of mass, and let us think in this way that we have learned the conservation of mass first with respect to a system, as we learn it first at school level. That what is that? For a system dm dt is equal to 0. We have learned it. Now you want to apply, it is implied system, the mass of a system remains unchanged. That means this is simply the equation of continuity if we use it for a system. That means the conservation of mass applied to a system gives this equation as simply the equation of continuity. Now if we apply the conservation of mass for a control volume, we take the help of Reynolds transport theorem. How? Here n is the mass, the property is the mass. So therefore the value of eta is 1. So with this concept, because eta is the property per unit mass, we write this, we will say that rate of change of mass for a system dm dt is equal to del T of, what is this, rho dV over the entire control volume plus rho v dot, sorry, dA over the entire control surface. And since by the law of conservation of mass this has to be 0, so therefore this plus this is equal to 0, which is the well known continuity equation in integral form, which is the well known continuity equation is integral. That is the time rate of change of mass within the control volume plus the net rate of mass efflux from the control volume is 0. Yes, at a boy at school level can tell what is the use of all this theorem, that everybody knows. This come from the common sense, that if there is a control volume fixed region in space where the mass coming in and going out, the balance must be accommodated by the control volume. But this may not be so from simple intuition for other laws, so that we have to invoke or we have to recall this theorem, what is known as Reynolds transport theorem, that relates the change in property of a system to that for a control volume. All right. Now let us see what happens for the conservation of momentum, which is not so simple. Conservation of momentum. Well, let us write the conservation of momentum. Conservation of momentum. Well, conservation of momentum. You know momentum may be linear or angular. Let us consider the linear momentum. Conservation of linear momentum, as we have done for Euler's equation, that is the conservation of linear momentum. Now let us first see that we have learned this conservation of momentum as we have really learned even from our school days with respect to a system, because all the statement explanation for conservation of momentum or laws of motion are given for a system. What is that? That is rate of change of momentum for a system, that mass into velocity, is equal to the net force, the total force acting in the same direction. This is precisely the conservation of momentum or equation of motion that is being learnt at the first stage, because the basic laws are always expressed in terms of the system. That means rate of change of momentum is equal to the force in the same direction. Rate of change of momentum of what? Of a system or a particle. So this is always implied. Sometimes a very tough school teacher may deduct marks if you do not write that. So rate of change of momentum of a system or a particle is equal to the net force, total sum of the forces acting in that direction. This is precisely for a system. Let us want to apply it for a control volume. Now then routine work is like that. What is n in this case is the momentum. Let us denote the momentum with a vector. So v is a vector momentum. So what is eta? It will be simply the velocity vector v, because by definition eta is the property per unit mass. In this equation you have to know all the nomenclature. So therefore we can simply write this d dt of mv, or we can write this way dmv dt for a system. This is for a system. For a system is equal to dmv dt for a system. Rather this looks very odd. d dt of mv, this way you write, for a system, all right, is equal to what? Del T of, now it is routine mathematical procedure, control volume, eta is v, rho, so we can write rho v bar dv, plus, please any problem you ask me, control surface, eta is v, so rho v, okay, v dot, this should be written like that. This is a vector and this is also a vector. This becomes a scalar, v dot ds. Simply I am writing this equation with the value of eta v and this. So this is precisely the Reynolds transport theorem, that means precisely the form of the Reynolds transport theorem for conservation of momentum. That means we are using the conservation of momentum statement for system and control volume with a equality sign with the help of the Reynolds transport theorem, which states physically that the rate of change of momentum of a system is equal to rate of change of momentum within the control volume plus the net rate of momentum a flux within the control volume. Net rate of momentum a flux within the control volume. So, well, this is the precise definition of the Reynolds transport theorem for the equation of motion. Now, what is this? This is nothing but the sigma f. So, therefore, sigma f becomes equal to, I am writing again this thing because this is so important, control volume rho v dv plus control surface v dot dA. So, this is what is known as momentum theorem. That means this is what is very important, known as, please, rho is missing, rho, correct. This is what is known as momentum theorem. This is what is known as momentum theorem. That means this is the equation of motion or conservation of momentum applied to a control volume. So, now onwards we will recall this formula, that the rate of change of momentum within the control volume plus the net rate of momentum a flux from the control surface across the control surface, that is from the control volume across the control surface, is equal to the net force acting the same direction, for which momentum we will take is equal to the net force acting on the control volume in that direction. Similarly, we can derive this for angular momentum, conservation of momentum, angular, conservation of momentum. Similarly, conservation of momentum, we can do it for angular momentum. Angular momentum, we can do it for angular momentum. Simple. In case of angular momentum, if we exploit this equation, what is our n? Is m times mass times, you know, the angular momentum is defined in this fashion, that this is the angular momentum of any particle or any fluid element about any point or a axis, perpendicular axis at a point, is the cross product of the radius vector. That means the, if you join these 2 points, then we get a radius vector, that r, and the velocity vector. That means physically it is the distance of that particular point from the point about which the angular momentum is considered times the velocity component perpendicular to this radius vector, which is denoted as r cross v. It may be v cross r with a sign change, that depends upon the sign convention, r cross v. This you know how the angular momentum is specified. So, eta will be r cross v. So, this is the only thing. Then again we write this thing in terms of the ddt of r cross v for a system is equal to del del t, eta is this one, that means first I write rho r cross v, this dv, well, plus over, this is over the control volume. So, over the control surface rho r cross v into v dot dA. So, therefore, we see that the rate of change of angular momentum of a system is equal to the, where is v is missing? Del del t, d dt of m is missing, del m is missing, not v is missing, m is missing, yes. So, correct, very good. Now, try to understand. So, therefore, this is equal to simply the rate of change of angular momentum within the control volume plus net rate of angular momentum from the control surface. All right. Now, again similar fashion, we have learned the conservation of angular momentum for a system first, and what is this quantity? What is this quantity? Torque. Very good. The rate of change of angular momentum to a system is torque. So, therefore, first plus second. So, this is the angular momentum theorem. That means the torque applied to a control volume must be equal to the time rate of change of angular momentum within the control volume plus the net rate of a flux of the angular momentum from the control volume. And obviously, for the steady case, this part will be 0. Similarly, for the steady case, for angular conservation of linear momentum, this part will be 0. The first part will always be 0 for this steady state. So, these are the very important theorem, angular momentum theorem and the linear momentum theorem, which will be discussed in analyzing the problem. Now I will come to the conservation of energy. Now conservation of energy. Now again, if we recall the conservation of energy, if we first start with the system, with the definition with respect to a system, we know the conservation of energy for a system is first given by the first law of thermodynamics. As we have already read at school, at the first year class, that conservation of energy and the first law of thermodynamics is synonymous. What is that? For a system. Now conservation of energy tells the total energy in the universe or in an isolated system which does not interact with the surrounding. Surrounding means anything external to this system is the surrounding. If we consider universe as an isolated system, the word universe is used in the physical science in a loose sense of an isolated system, that it does not interact with anything outside. That means in a universe or in an isolated system, total energy remains constant. So systems, there are many systems within the universe or an isolated system, they are interacting with their surroundings. So therefore, if we define this conservation of energy for an interactive system, system interacting with its surroundings. Surroundings means everything external to the system. There may be number of systems which are external to a particular system on which we are concentrating our attention. So therefore, we can tell that for a system interacting with surrounding, the conservation of energy is obvious, and it comes again from the physical intuition from our school days, that the total energy remains constant means the net energy interaction by the system with the surrounding must balance with the energy contained in the system. With the energy contained in the system. And as you know, or you will read afterwards in more detail, that thermodynamics first law gives the two distinct status of energy. One is the energy in transit, which always occurs in transit, for example heat and work, and another is the energy which is contained or stored in a system, which is known as internal energy. So therefore, the total energy interaction by a system in the form of heat and work with the surrounding must be balanced by a corresponding amount of internal energy stored in the system. That means in a process, if a system exchanges energy and it gives energy to the surrounding, so its internal energy will be decreased. Or if takes energy from the surrounding in a net energy interaction process, its internal energy will be increased. So therefore, the first law of thermodynamics for a system, which is the law of conservation of energy applied to a system, which we learn at the basic level, can be written like that. Please see that if there is a system, and if we consider in conventional positive sense that a amount of heat delta Q is added to a system, and the system does an work delta W, and by doing so, if the system goes for a change in energy delta E, internal energy E, then from the first law of thermodynamics or the law of conservation of energy, whatever you call, delta Q minus delta W, this is the net energy that system has gained, must be equal to the increase in delta E. So this is the conservation of energy. In thermodynamics, we will see that all kinds of energy interactions is divided into heat and work. This work takes care of all kind of energy interaction apart from heat. That means this will be mechanical work, this will be magnetic work, this will be electrical work, all kind of work. So heat and work, this difference is equal to the energy change in internal energy. That means heat added to a system minus the work done by a system is equal to delta E. For a finite process, you can express, this is a differential expression, is, well, this is dE, rather we call it as dE because differential is dE. This is the finite delta E, finite change, it call it dE, Q minus W is daily. Now on a rate basis, if you write, we are more interested on a rate, that is the rate of change of Q for a change in time. That means if delta Q is added for a interval of delta T and delta W for an interval of delta T. So it is the rate of heat addition and this is the rate of work done. As you know that heat and work are the path function, they are not the point function, we cannot write in a strict differential sense. So del Q del T minus delta, the rate of heat added and the rate of work added, work done. That means delta Q for a time delta T, delta W for a time. So this is equal to dE dt, which simply can be written in a differential manner with the real spirit of differential from mathematics, that means the rate of change of internal energy with time, because internal energy is a point function. So this is the time rate basis, the first law applied to a system. Now if I use the Reynolds transport theorem, Again, if we recall the Reynolds transport theorem, what is this Reynolds transport theorem? That d and dt. Again, if we write the now Reynolds transport theorem, so d e dt, sorry, big D, I usually D follow, d e dt for a system. What is this? Del del T of control. What will be eta? Let E, where E is the internal energy per unit mass, where E is the internal energy per unit mass. Without knowing the explicit form of the energy in terms of other parameters, we cannot write anything either for E or E. So, we define small e as the counterpart of big E per unit mass. It is a total energy, total internal energy per unit mass. So, therefore, this simply becomes equal to dV plus, what is this? Please tell me, any problem? Eta is E rho, absolutely simple. So, this is the, that means the right hand side represents the rate of change of internal energy within a control volume plus net rate of efflux of energy from the control volume across its control surface is equal to d dt for a system. So, what is d dt for a system? Open it, because what we have learned first. So, you see my way of approach. First, we see what we have learned for any conservation law with respect to a system, then using the Reynolds transport theorem. So, this is replaced by del q del t minus del w del t is equal to del del t of, well, del del t of Cv E rho dV plus Cs rho V dot dA. Well, so this is precisely then the conservation of energy applied to a control volume. This is the conservation of energy applied to a control volume, which tells that the heat added to a control volume, the rate basis, the rate of heat added to a control volume minus the rate of work done from a control volume is equal to the rate of change of energy within the control volume plus the net rate of efflux of energy from the control volume across the control surface. This is known as general energy equation, general energy equation of a for a control volume, for a control volume, for a control volume, general energy equation for a control volume. Now, next task is that this energy equation is well known for a control volume. Next task is to recognize what is the internal energy E here, because here also I have forgotten to write E, E has been. So, what is this E? That means, what is the internal energy which is associated with a flowing particle, because this is going out when it is going across the, when it is flowing across the control surface. So, our main task is now to recognize the internal energy. Okay. So, after this mathematics, I think we should now physically try to recognize physically what are the different forms that a fluid element or a fluid particle possesses when it is in flow, in course of flow. Because if you consider a control volume, so definitely when the fluid particle crosses its control surface, comes into control volume, it brings it with it some energy within the control volume. Similarly, when it is going out, a fluid particle or a lump of fluid system going out of the control volume, it takes away energy from the control volume along with its flow. So, therefore, now it is essential to recognize what are the different forms of energy that a fluid particle possesses or a fluid element possesses by virtue of its flow or in course of its flow. What are those energy? Can you tell what are those energies? One is the first, for any system under any condition, the energy possessed by it is the intermolecular energy. That is the energy by virtue of the kinetic and potential energies of molecules comprising that substance. So, one is the intermolecular energy. Another energy is the kinetic energy. This is because of motion. So, when any particle is in motion, whether it is a solid particle or fluid particle, by virtue of its motion it has an energy which is the kinetic energy, whose magnitude is given by mass times the square of velocity by 2, mv square by 2. That is the potential energy, and another one is the which is the kinetic energy, and another one is the potential energy. What is the potential energy? Please define what is potential energy. What is potential energy? So much about potential energy you have read at school level. What is potential energy? Please. Yes, very correct. It is the energy which a particle or a system or an element possesses by virtue of its position in a what type of force field? By virtue of its conservative force field. Yes, by virtue of its position in a conservative force, because work is done to place the body at a particular position in a conservative body force field. If it is the only gravity as the conservative body force field, we know the value of the potential energy is mgh if we consider h is the height from any arbitrary datum level where we take the energy to be 0. That means from that level to bring the particle at a level height h, the work mgh is being done. So this is the potential energy. Apart from that, there is another energy known as flow work or pressure energy, which I will discuss in the next class. Time is up, so we just finish it here for today. So next class we will be discussing another form of energy along with these three forms, which appears for a flowing particle of fluid or a flowing element of fluid, that is pressure energy or flow work. This I will discuss in the next class. Thank you.